Good morning, everyone. Thank you all for joining our virtual presentation. Today, I'm going to present a novel theoretical framework for unifying the physics of active and passive matter for certain applications. Now, as we all know, statistical mechanics or statistical thermodynamics is the intellectual framework for predicting the macroscopic properties and the behavior of a system of millions of passive agents, such as molecules. Now, by passive, what we mean is that the agents are not goal-driven. Molecules, for example, do not pursue goals and they do not make decisions. They are simply prisoners of Newton's laws and conservation equations. Now, what would statistical mechanics look like if the agents are goal-driven? Now, answering this would lead to a new theoretical framework for active matter, including rational agents such as humans and their economic behavior, as we shall see. Now, we outline such a theory in this presentation. We call it statistical teleodynamics. It is the statistical mechanics of goal-driven agents. The name teleodynamics comes from the word telos, which means goal in Greek. Now, we claim that the main conceptual difference between active and passive matter is the pursuit of goals by the active agents. This naturally leads to the pursuit of utility and the strategies for maximizing it. So we propose that a game theoretic framework is the appropriate way of looking at these utility-driven agents. Now, we consider the population game framework, particularly the potential games approach, where n agents are competing, for example, for a job in a market or in a game of some sort. And potential games informs us that there exists a potential phi such that the gradient of the potential, which we see here, is the utility H sub I. Now, there exists a potential games also tells us that there exists a unique Nash equilibrium when phi is maximized subject to certain constraints if the potential is strictly concave, which is the case in our applications. Now, with this new perspective, we can actually look at thermodynamics as a game of passive agents, okay? So now for molecules, I can propose utility, quote unquote, of course, because strictly speaking, molecules don't have utilities, but it can be thought of as if they have this kind of a utility shown in this expression. So this is the utility of any molecule I, which is in energy state E sub I, and it is competing in the same energy state, it is competing with n other molecules. So that's n sub I. And it is given by the Boltzmann factor beta times E, that's energy again, and natural log of n. And from this, we can actually integrate that and get the potential, and it turns out to be this expression, okay? Now, to obtain the equilibrium behavior of molecules, we maximize this potential subject to these constraints of conserving the number of molecules and the total energy constraints. And so this is the Lagrangian formulation. And then you get the game theoretic equilibrium, which is a Nash equilibrium. Remember, this is a game theoretic perspective. So the equilibrium you get is a Nash equilibrium, but it turns out to be the same as the statistical equilibrium. And in fact, you get the Gibbs-Boltzmann distribution of energy, that famous exponential distribution is recovered. The key insights here are that the potential phi is essentially the entropy in statistical mechanics. And the molecular utility is kind of like negative chemical potential. And at equilibrium, all molecules have the same utility, which is equivalent to, in thermodynamics, all molecules having the same chemical potential at equilibrium. I've skipped over a lot of the details, which are to be found in the references I've cited below. Now, switching gears and going to the other extreme, what about the income distribution of rational agents now? So we now looked at agents which are not goal-driven molecules. Now we are going to look at a population of agents which are all goal-seeking, so which are like people in a market, for example, in a job market. So here we can define an effective utility for an agent as H sub I, which depends on salary SI and the number of people competing for that job in that salary level ends up high. And it is given by this expression. Again, the details are to be found in the references I listed. So it depends on the log of the salary, and then the negative beta log is squared and gamma log ni. Now, to determine the equilibrium outcome, we maximize the potential again and subject to constraints. And then we get the equilibrium distribution, not an exponential distribution this time because the objective functions are different. We get a log normal distribution. It is the equivalent of the Boltzmann distribution in economics. So this is the income distribution in an ideal free market society. And what about the utility of everyone? Well, since it's an equilibrium, every agent should have the same utility, which indeed is the case. So if you compute the utility H star across all along the log normal distribution, this is the log normal distribution, it is the same for everyone, H star. And so right from the janitor to the CEO, the salaries are different, but they all enjoy the same utility. The janitor may make a low salary, like $30,000, and the CEO may make a $3 million salary, but their effective utilities are the same. So in that sense, it is the fairest outcome that is possible. Now, okay, so the same unifying statistical teleodynamic perspective predicts the equilibrium outcomes of a population of passive agents, and we get the Boltzmann energy distribution, and rational goal-driven agents, we get the log on normal distribution of economics. So this is all physics and this is all economics. And it seems to unify both these fields by maximizing the game theoretic potential subjecting to constraints. Now at equilibrium, all agents have the same utility. So that is the equilibrium condition. Now the molecules, you can think of them as 0%, you can think of them on a spectrum where they are at one extreme with 0% strategic capabilities and they are not at all goal-driven. And people at the other extreme with 100% strategic capabilities and completely goal-seeking. So what about things that are in between? How about active matter that are in between these two extremes? One possibility, one population of such things we can consider are ants. Let's look at ants. Now it turns out, ants are, in some sense, certainly ants are more. They have more decision-making capability than a molecule, in the sense they seem to make certain decisions based on their immediate needs, unlike molecules. So they are in this spectrum somewhere in between the 0 and 100%. And if you look at ant crater formation, where in the hole down below, under the ground, there are literally thousands, hundreds of thousands of ants which work together cooperatively and then get the sand or grains under the ground out so that they can form colonies underneath. And the ant crater, which, this is an actual ant crater, it looks like this. It is axisymmetric, as you can see, it is symmetrical over this axis. And the dynamics of this involves transporting grains and then taking them outside the colony, outside the hole, and dropping them off. Now, ants move outward, typically they move outward with some average velocity v, and the propensity for an ant to drop off a grain increases the farther they go, because they're carrying a load and they really want to get rid of the load as soon as possible. And that can be modeled by this simple equation. Now, Picardo and Pushpavanam approached this problem with a continuum model for crater shape formation, using some basically like a grain balance equation, input minus output equals accumulation sort of a deal, in a continuum formulation. And this leads to the number of ants at any distance r away from the crater, governed by this kind of an exponential distribution. Now we can look at the same problem from our framework of statistical teleodynamics, where we think of ants as active agents making decisions and trying to maximize their utilities. Now, basically, ants have, the utility of the ant or the effort by the ant depends on two factors. One is the work it does by actually carrying a piece of grain or a piece of sand outside. The work depends on how long the ant has to take that And the idea is to take it as far away from the hole so that the sand doesn't fall back into the hole. At the same time, the farther you go, the more work you're doing, which the ant would like to minimize. And that is where they are active, in the sense they are trying to minimize the effort, minimize the work, and thereby, the negative of the effort is utility, thereby they're trying to maximize their utility. And so how long the ant takes to drop off a sand can be modeled by this equation. It's basically, how far it has to travel times time. And then it is, the R is the distance, A is some parameter, and omega is this factor K over V, where velocity is the average velocity of the ant travel. So the ant also attempts to also minimize the competition, because wherever it wants to go, it doesn't want to get crowded by other ants rushing to the same place. So it has two, basically, it's trying to minimize two things, which is the amount of effort it has to do, and then minimize the competition. And the competition is the number of ants at any given place is given by this. This is the ant density times, if you consider an annular ring around that space, that'll give you that. And so this can be modeled, converted to your disutility using this kind of an expression. So now the net utility for the ant is basically, sum of two negative items, because the utility is a positive thing, and then the work and the effort and the competition, they are negative things. So you multiply them by negative in order to make it a positive quantity. So by maximizing utility U, it is basically trying to minimize the work or effort and then minimize competition. Now these two expressions become that. And then at equilibrium, everybody will enjoy the same utility. That is, this U will be the same for all ants. And so by making this U star, and that is equal to this, we can get the density expression in this format. And this turns out to be the same distribution obtained by Picardo and Pushpavanam in using their continuum formulation. So the cumulative distribution of grains is obtained simply by integrating overall volume, and that is the capital F of R, and that turns out to be the Weibull distribution, which has been actually observed in practice. And this is the behavior of these density functions as a function of this parameter alpha. As alpha increases, the ants travel farther and farther, and similarly here, as omega decreases, the ants go as omega decreases, the ants travel farther and farther, because omega is the inverse of the velocity. So as the velocity increases, they travel farther. So it has, the behavior is kind of expected. So how does maximum entropy formulation essentially result as the equal utility formulation? So the maximum entropy formulation comes to us from statistical mechanics. Equal utility formulation comes to us from game theory. It turns out these two are actually very deeply connected. So the maximum entropy formulation is this for the thermodynamic game. This is for molecules. So this is your maximizing entropy subject to these constraints, so mean energy and total number of molecules. And you do the Lagrangian formulation, and then set this gradient to 0. You get this expression to be a constant. And this turns out to be the equal utility that we saw in game theory. And so equal utility across phase space is equivalent to maximizing entropy subject to constraints. And the same thing happens with the ant crater. So this is the maximum entropy, and then out comes the distribution. And so to summarize and conclude, we proposed a novel theoretical framework that unifies the statistical mechanics of passive matter with game theoretic approaches that are appropriate for active agents, such as people, for example, and or living agents like ants. And in that sense, it is unifying certain aspects of physics with certain aspects of economics, and even sociobiology of simple creatures such as ants. Now, there is a deep connection, which I'm not gotten into, which is discussed in the references I cited, between statistical mechanics and potential game theory. And essentially, the game theoretic potential turns out to be entropy in statistical mechanics under certain formulations. And this is a previously unknown and a surprising connection. And this explains crater building behavior of ants as utility-driven activity. as a goal-driven activity. And so ants too try to maximize utility and reach equilibrium. So let me stop at this point and thank you again for your kind attention. And we'll be happy to answer any questions later on in the session, or you're welcome to contact us by email. Thank you.